Hey, thank you very much for the kind introduction, Francois, and good morning, everyone. It's a great pleasure to be here today. So as Francois indicated, I'll be talking to you about unconventional computing architectures for machine learning. And just to set the scope right, when I say unconventional, I don't mean quantum computing or chaos computing or any of that. I'm talking unconventional in the sense of not traditional von Neumann architectures. And we go towards those because, exactly like Francois said, to enable the deployment of machine learning in energy-constrained compute environments. But before we go there, just let me provide you with a little bit of background. That's important to understand, so you know where I'm coming from. So as indicated, Xilinx is a semiconductor company. We're fabless, founded over 30 years ago in Silicon Valley. And most importantly, we're famous for inventing the FPGA. So who of you know what an FPGA is? Whoa, that's really good. So that's a lot. That's actually 80% what I've seen here. So this is what the first FPGA looked like, shipped in 1985, and it had 128 free input lots. And if you look at the devices today, they would have millions of 6 input lots. So it grew like by 6 orders of magnitude. Now for the 20% who haven't raised their hand, and I assume that you were not shy or anything, you don't need to know much about FPGAs to understand what I'm talking about this morning. The one thing you need to know is it's a customizable, programmable hardware architecture. So I often compare it to, it's the chameleon amongst the semiconductors because it can be anything. It can be a piece of memory, it can be a processor, you can customize the I/O, you can make it fit whatever is your need. The classical use case, because of this, is you use it when nothing else works. So let's say you have a board design, and where you see the question mark, you want to fit a chip in there. And there's nothing on the planet that will fit in there. So what you have are two options. One is you build your custom ASIC for going into there, or the second option is you use an FPGA. So you use the FPGA when nothing else works, and you really don't want to build a custom ASIC because that's very risky, takes ages, and costs a huge amount of money. So the more recent use case for FPGAs, which has emerged maybe in the last few years, and we're very happy about it, that people actually start using FPGAs in order to achieve, through customized hardware architectures, higher performance or better energy efficient. So you remove everything from the chip that you don't need. You customize the compute to exactly the arithmetic that is required to implement the functionality that you need. So this is exactly what happens in the context of machine learning. So because it's the chameleon, and it can go anywhere, FPGA are deployed in dishwashers and perhaps more exciting applications such as Mars rovers. They're basically everywhere. And from my point of view, I am part of the Xilinx research organization, which is a minuscule part of Xilinx. If you saw on the earlier slide, 3,500 people worldwide. Xilinx research is 1% of those, 35 researchers worldwide, and there is, in fact, 8 of us sitting here in the Dublin Labs, which is out in City West. This is City West on a nice summer day. Doesn't often look like this, and this is part of the gang that you see. And we have, since 1 year, funding for the expansion of an AI lab, so research specifically dedicated to AI. Which we're slowly growing. So we'll be adding more positions over the years. This is the current labs team. So 8 of us. We have, in addition, 2 people working in the university program, Colin and Katie. And also, if I may say so, we have a very active internship program. If any of you are ever interested in doing really cool research with FPGAs, we take on average 4 to 6 interns at any given time. They come from all over the world, from the US, from Australia, from China, from Italy. We even have some Irish people too, but it's actually really multinational. We are always looking for talent. The internships go 3 months to 12 months, depending on how much time is available. And over all the years, I'm with Xilinx 12 years, I think this is already outdated. I think it's over 70 interns that came through my organization. Many collaborations came from this, and many actually found employment too. Anyway, that's enough on the background. Let's talk about the context of machine learning and what's happening there. So for me, what's happening at the moment is perfectly visualized by this Calvin and Hobbes comic. You guys are probably too young to read Calvin and Hobbes, but it's a very nice comic. And it might be a little bit hard to read from the back, so let me just walk you through it. First picture, here comes the sports car at 200 miles per hour. Second one, here comes the cement truck, look out. And then comes the inflammable chemical truck, and this ought to be good, right? And this is exactly what happens here. So the machine learning trends hit the technological reality. And let's go in smaller steps on what's actually going on here. So let's take a look at the sports car. So that's the sports car, machine learning. So since the end of the 18th century, as you all know, we are undergoing one industrial revolution after another one. And currently we're in the fourth one, which is all to do with the rollout of machine learning algorithms. And as all the previous one, they come with a huge amount of promise and potential, right? For example, machine learning promises to solve the unsolved problems, according to Jeff Dean from Google Brain. You can address the grand engineering challenges of the century, such as making solar energy economical, finding cancer cures or whatnot. And also comes with a lot of fear. You know, Elon Musk worries about the rise of the killer robots, the AI apocalypse. And while I'm a really huge Battlestar Galactica fan, I'm not going to talk about killer robots right now. So I really want to focus on talking about the potential of the technology, what it can and can't do, and most importantly, what are the challenges actually associated with it, and how we as computer architects can actually help enable the rollout into the self-driving cars and so on. So I think many of you are familiar with all of this, but just to disambiguate the terms, so AI is the science around enabling machines with cognitive functions such as learning and problem solving. It's a huge spectrum of algorithms. Subset is machine learning, which gives the computer the ability to learn by itself without actually being explicitly programmed. And that already has this hint towards that there's these two phases going. There's a training phase where the machine learning algorithm learns, and then there's the deployment phase. That's when you actually put it into action. So this is kind of important to understand from the concept as we go through the compute requirements. So in the training phase, I take my algorithm, I expose it to training material. So lots, for example, for image classification would be lots of pictures. So let's say I want to train this thing to recognize a dog, so I give it loads of pictures of dogs. This is typically computed in the cloud because it's humongous in terms of compute. And once it's trained, I deploy it. Deployment often at the edge in IoT and automotive and so on for inference. So this is when I'm taking the trained model and I expose it to something that it has previously not seen. So another cute doggy picture, and then hopefully it gets to the right answer. So the predominantly used algorithm to, I would say, probably about 90% of the machine learning algorithm spectrum are neural networks. And just also a quick recap from a computational point of view. They are usually feed-forward computational graphs, apart from the current neural networks, constructed from one or more layers. Typical neural networks can have up to thousands of layers, right? They can be humongous. And in each individual layer, each layer consists, you see that at the top right-hand side. Do we have a mouse? No. Give me a sec. Let's see if we can get a pointer. Okay, so each layer typically consists of a set of neurons, and each neuron is connected via synapses with the outputs from the previous layer. And each synapse is associated with a weight. So the compute that a neuron does is typically a linear transform of the receptor field. So let's say N0 depends on the outputs from the previous layers, so I0 and I1. And in order to compute N0, I multiply the synaptic weight W00 with I0. add the next one, which is W01 with I1 and so forth. So it's basically lots of multiply accumulates, and then I take the whole lot and throw it through a nonlinear activation functions. Now, often people ask me, why is it nonlinear? And the answer is simple. If it were linear, everything, all the layers would collapse into a single one. So this is, and then we're back to shallow learning. I'm not sure whether you came across shallow learning in your curriculum, but this is basically where we had one layer that we were learning. So, and everything else was done manually. So for example, for recognizing a cat, you did manual, there was actually a science around feature engineering describing the features of the cat. So it could, for example, be pointy ears or slanted eyes. You encode the results in a vector and you feed that into your classifier. The classifier during training then learns to what extent you need to have pointy ears and slanted eyes in order to be a cat. Now, that was 30 years ago. Is that accurate? It's a long time ago anyhow. Since then, we've migrated towards hierarchical learning, so this is where the deep concepts come in, where we actually learn from low-level features to the high-level features. So if you take your computer vision comparison, right, you would first learn the edges, then the textons, then the parts, and then the objects. And every aspect of this implementation, all the layers are actually learned during training, not just the classifier. So why are these convolutional neural networks so very popular? And in my head, there's basically 3 reasons. First, they require little or no domain expertise, which means you don't need to have a clue about the problem that you're solving, right? Which is very nice. Secondly, neural networks have the theoretical property of being a universal approximation function, which means the scope of problems that you can solve with this is essentially infinite. And finally, if you make it big enough and you train it hard enough, you can outperform humans on specific tasks. So, for example, the very popular ImageNet competition, right, since 2015, the machine learning algorithms outperform the humans. And if you listen to Elon Musk, 2020, AI is going to outperform us on absolutely everything. Whether you want to believe that, I leave that to you. Fact is, though, neural networks will increasingly replace other algorithms. We see this everywhere, unless, of course, there's an algorithm with very simple rules that can describe it. Secondly, it can solve problems previously unsolved by computers, right? Recognizing cats and dogs since 2 years. Third, it can solve completely unsolved problems. And that's when it gets very, very interesting. So, but let's go into more detail on what actually happens with a neural network during inference. And I want to do this just in order to get across the huge amount of compute that is actually associated with this. So let's say I take a ResNet 50, which is probably one of the most popular benchmarking neural networks out there for ImageNet classification. So the network sits in the middle, has 70 layers in reality, even though I didn't draw them all. I start off and I feed it one image of one little doggy, and it propagates basically from one layer to the next, and the neural network ventures a first guess. I say, maybe it's a cat. Doing this took 7.7 billion operations. It's humongous, right? It also has a humongous memory footprint. We're talking about over 25 megabytes of weight storage, so all the parameters in a neural network. So it's crazy. So that's just for feeding one image through, as you would do during inference. So during training, what I do is, I know what's in the picture, so I feed the result back to it. So I tell it it's a dog. The neural network computes the error, and the error back propagates through the neural network and updates all the weights. And doing this takes 23 billion operations, right? This is another factor of 3 in terms of compute that is required. That is a lot, right? So what's more so, I can't train a neural network just on one image. So for ImageNet, for example, I have to work with 1.2 million images. So now you have another factor of 10 to the power of 6 in terms of compute that I pack onto this. So now we're talking about peta operations. And as you probably know from the course, I don't just run it through once. I have to go through learning rates, adjustments, all the hyperparameter adjustments. So let's say I run 100 epochs of training through this. Gives me another 2 orders of magnitude, and now we're talking exa computing. So this is high performance computing, literally, that is required here. And so in short, the sports car, coming back to this, humongous amounts of compute, right? So let's take a look at the cement truck. Explosion of data. So I'm sure you heard about this as well, right? So the big data problem. So the planet in itself is producing an astronomically growing amount of data. That's caused by all the new sensors that are being rolled out. Think of all the sensors that are going into cars now to enable driver assist or have them self-drive. Think about all the sensors that are going into the buildings. Think about all the health sensors people put everywhere on their bodies to monitor heart rates, temperatures, and whatnot, right? More, and each of these sensors produces data. On top of that, we have an increasing number of users. And finally, we have more and more use cases. And actually, one of the most surprising one I came recently across is genomics. So genomics data is actually expected to outgrow, for example, the amount of data that's stored on YouTube, which is already a pretty vast amount. So what is genomics used? Well, you probably came across resurrecting dinosaurs in Jurassic World recently. So, but it's more seriously used for archaeology. It's used for space exploration, where they take probes from planets and analyze life forms. It's used in medicine, cancer research, genetic diseases, ancestry, paternity tests. Yeah, it's crazy, right? So that is even, by a factor 10 more data than YouTube. And all of this data that we're producing is unstructured. And in order to try to make sense of it, the hope is that we just throw a lot of machine learning algorithms at it and we figure out what it's all about. So that's your cement truck. So then we talk about the inflammable chemical truck. So this is now more my territory. So this is technological reality of where we are today. Who of you has heard about Moore's Law? Oh yeah, very good, right? And I hear about it every day. This is our biggest #1 problem in the semiconductor industry. And and while we still know on how to shrink the technology nodes and make the transistors even smaller and smaller, with every bit that we shrink it, it becomes more difficult and it becomes more expensive. So if you look at, for example, 3 nanometer technology, there is talk about not using silicon anymore. So we're going to esoteric materials such as graphene. There is the technological aspect to it, but the bottom line, the American multinationals, all they care about is the money, the cost of this, right? As you go more speculative and the yield goes down and more esoteric material, it becomes expensive, and that's the biggest problem, right? And in fact, this has already happened since 28 nanometers. 28 nanometers is a few years back. This is our Vertex 7 series. We have since then run Ultrascale, Ultrascale Plus, and now Everest coming out, right? This is already past, but since 28 nanometers, the cost of the transistor has been on the increase, which makes the economicals of this whole thing questionable. So there is no incentive for Xilinx of shrinking. So let's put it this way. The second problem is the NARD. So the NARD had said a long time ago that if you shrink transistors and you pack more of them together, the power density on the surface stays roughly equivalent. Now, that hasn't happened. Since 1990, we've been actually, the power density has been on the rise, and this is from Intel, the graph. It's actually a pretty old graph at this stage. Predicted that round about now, we would be hitting the sun's surface on top of the Xeon processor. And that hasn't happened, but it's hot enough to fry your breakfast, right? So power dissipation is a second problem, and you might have heard for dark silicon and stories like that. Very real, right? This is the other issue of packing more transistors into the devices. So semiconductor industry is stretched to the limits of what they can actually build or not incentivized to build. And on the other hand, we have humongous compute and memory coming towards us. So this ought to be good. And it is, right? Because what happens is as these technologies hit each other, there is an explosion of new computer architectures coming out of it. So we cannot do this with standard von Neumann architectures anymore. We're hitting this era of heterogeneous compute where we use customized accelerators. So computer architecture has never been as exciting as it is at the moment. There's so much innovation happening. So let me give you a few examples of what's going on. First of all, the cloud, right? So the cloud used to be, a few years back, just processors, huge amount of processors and huge amount of storage in the back. Since a few years, first they introduced GPU nodes, right, in particular for training acceleration of neural networks, and since 2016, there's FPGA nodes in the cloud. So the cloud in itself becomes heterogeneous. But it propagates all the way down to the device level. So I'm just showing you an example from my world, from the Xilinx world. As, remember the FPGAs? Well, they're changing as well, right? They're evolving, and they're no longer a homogeneous sea of gates. What we have now is, now the latest CEO termed the name ACAP. I'm still getting used to this, but and it's true. I mean, when you look at this is no longer an FPGA. What we have now, we still have our chameleon fabric at the bottom, but in addition, we have now the AI engines, which are ReLIW processors, which are customized for the compute of machine learning arithmetic. Everything is interconnected with an NOC. We have application processor in addition. We have real-time processors. We have DRAMs packed into it with HBM stacks. We have analog mixed signal. So yeah, it has fundamentally changed in the way our devices look. And in particular for AI, which is incentivized by the humongous volume requirements, as well as by the cloud dynamics, there is an immersion of a huge spectrum of customized hardware for AI. Microsoft termed the name Deep Learning Processing Unit, or DPU for short. I like it. I think it might actually stick. So you have many silicon startups in this space, Knupath, Wave Computing, Grok, Cerebras, Iris, Nirvana, you name it. And perhaps most prominently, Google built even an ASIC, which is the Tensor Processing Unit, or TPU for short. So those are the ASICs for AI acceleration. So now really unconventional, there are some quantum computing approaches in there as well from a startup called D-Wave. And, but coming back more to less unconventional approaches. So you have the custom AI solutions, which are the hard DPUs. We also have soft DPUs, where you basically build custom accelerators on FPGAs. And Microsoft has that done with their Brainwave project, and we're doing a lot of that as well. So let's take a look at the DPU architecture. So, so at the top left, again, you have your typical convolutional neural networks. And at the bottom right-hand side, this is from a very high view what a DPU would look like. Now, this is a crude simplification, so take that with a pinch of salt. But what you have, in essence, is a matrix of processing engines. You have some sort of memory subsystem connected via a DMA engine. You have the compute customized for AI, right? So there are specific operations implemented on this, and you have a certain amount of on-chip offering. So it's really crude. The way it computes is it takes the first layer and schedules it on top of the matrix of processing engines. So it parallelizes all the compute of one layer across the matrix of processing engines. Then it computes the next layer. So it's kind of a sequential layer by layer compute, but it parallelizes the compute within one layer, and it customizes the arithmetic towards machine learning. So that's kind of the first way of going more unconventional. But we can do way more than that when you go into an FPGA. So what we do is we actually custom tailor the entire hardware architecture towards a specific neural network. So again, at the top, you have your neural network with your layers, 7 layers I'm showing here. In reality, these layers all look different, right? They have different types of compute requirements and different types of memory requirements in each of the layers. What we do in the FPGA, we literally pour the neural network into the FPGA. So it's kind of a one-to-one mapping of the neural network inside the device. So we custom tailor the architecture, and we custom tailor it to the extent that not only that we have all the layers instantiated, but that we also map the compute resources of each of the layers towards the compute requirements in the neural network. So if the first layer takes 10x the compute, I give it 10x the amount of compute resources inside the device. And what I have then is a balanced data flow. So I can actually then, all the layers process the images at the same rate, and I can just back-to-back stream my images through this accelerator. So compared to the one on the previous slide, what this one does, it's actually parallelizing not only the compute within a layer, but also the compute across all the layers. It's basically pipeline parallelism that we're doing here. So now we can do that in an FPGA. You can't do that in an ASIC. And the reason is simple, because it does exactly one neural network topology, right? If I change the topology, I have to redesign my FPGA design. I have to parameterize it differently and change again. Whereas the one on the right can compute any neural network. So it has the flexibility, but it loses in efficiency because the one on the left is custom tailored to your specific topology. The one on the right will lose efficiency depending on how well balanced your neural network is. You might have a really small layer which just uses one processing engine, and I have a very large one. So depending on how balanced your topology is, the one on the right-hand side can be very inefficient. So all of that at the expense of the flexibility on the left-hand side, and also perhaps worth noting is the data flow has no control flow associated with it, right? This is very simple. Everything is hard-coded, basically. You just stream your stuff through, whereas the computer efficiency is basically a control flow or a scheduling problem on the right-hand side. So that's kind of the spectrum of options that you have. But we can go even more unconventional, right? So now we've just parallelized the arithmetic within a layer and across layer. Now let's take a look what can we do actually with the arithmetic itself. And the beauty is since a few years there's a lot of research gone into that shows that you do not need floating point compute for neural network to achieve high accuracy. So this graph here shows you accuracy, well, error rate on the left-hand side. So you want to be really low. You want to have 0% error, so really low on this corner. On the x-axis, we have just time. And we've been tracking the accuracy for ImageNet classification. This is top 5 error here over the years. And you can see since 2010, when we were like 27%, it's come down an awful lot. And we're now down, I think, somewhere around 3%. What you can see on the orange floating point line is that the improvement becomes smaller and smaller, right? The floating point improvements are slowing down, and they come at incredible compute cost. I'm not sure whether you talked about ensemble techniques and things like that, but this is something they do in order to get like another fraction of a percentage improvement in error rate. What they do is, for example, they take the same neural network and they seed it differently during training, deploy it 1,000 times, and then average the results. So if you think in terms of compute, now I'm adding another 10 to the power of 3 to the amount of compute they already have, which is insane, which means anything down here is nothing that you can actually deploy within an embedded environment. You have to see compromises, right? This is unrealistic. You cannot stick your 100 GPUs in the back of the car in order to get another % of accuracy. So what's been done is we're using reduced precision compute. So we're going to fixed point arithmetic, which is fundamentally smaller in terms of footprint to implement. And it obviously uses less bits. So the gray ones is reduced precision, and when I mean reduced, it's 8 bits and lower. So we're talking a few bits for each of the data types instead of a 32-bit floating point representation. The yellow dots are the ones that we've actually trained in-house, and the blue line, those are the extreme variants. Those are actually fully binarized neural networks. So there's actually 1 bit per neuron, if you think, which is actually very hard initially to understand that can really work, but it does. Okay, so let's first talk about the benefits of reduced precision. So I hinted at this already, but it fundamentally reduces the hardware cost per operation. In fact, between a 32-bit floating point and a binary operation, there is 100x in terms of compute resources inside the device that I can save. So if this would be, the matrix here would be the size of the footprint of a floating point addition, the binary addition would look like this, right? So it's much, much smaller. Now what happens is, if it's much smaller, I can instantiate many, many more of those, right? Which means I can scale the performance of my device exactly by that factor that I've shrinked it. And that only works because neural networks are incredibly parallel. Otherwise, I wouldn't be able to take advantage of it. The second part is it shrinks my memory subsystem, obviously, right? So if I take my ResNet 50 at floating point, 32-bit, it will take over 100 megabytes. If I go to 1 bit, it takes 3 megabytes. 3 megabytes I can fit on chip. I don't need external memory, saves power, saves memory bottlenecks and whatnot. Life gets very sweet when you don't have to go off chip. So those are the first 2 advantages. The third one is it inherently saves power. So the top right-hand graph is from Stanford University, from Bill Daly. They looked at the energy cost of individual operations. So you have, for example, a 32-bit floating point addition takes 0.9 picojoules. If I go to 16-bit floating point, I halve the energy cost of that operation. So reducing precision here saves, but also going from floating point to fixed point saves. So if you go floating point 16-bit to 16-bit fixed point, you save an order of magnitude. So there's significant power savings again, which then translates on how far you can go before you have to hit charge up the car again. So this is for ASICs. This is for FPGAs. FPGA is the same thing. You have the power consumption on the x-axis, and this is the same neural network. It's actually an LSTM, so a recurrent model, which we trained with 8-bit, 8-bit. Then so 8-bit weights, 8-bit activations. Then we took it down to 3-bit weights and 8-bit activations, and so on. And at the top left is 2-bit weights, 2-bit activation. You can see the power shrinks. Now, it also hints at the problem with reduced precision, which is that the error rate goes up, right? So there's no free lunch here. So let's talk a little bit about what the compromise looks like. Okay, sorry, we'll pause the thought. We're going to talk a bit, taking unconventional, the last step forward. Here's another thing that we started doing and that we've also seen in the research community happening. It's that we actually start now not only to parallelize within a layer, between layers, and shrinking the precision, but we also parallelize the compute across individual bits. So in order to explain this, I drew this up. I hope this helps clarify it. So if you look at your standard processor architecture, your ALU would take 2-bit vectors, combine them, and spit out an output. So you compute what we call bit parallel. So you put A and B in, you get an output. This is how it happens. So there's a different way of computing. It's called bit serial. What you do is you actually shift your operands in serially. So that's on the right-hand side. So I've basically serialized my incoming operands, and then I compute them 1 bit at a time. So this is what's called bit serial. And what happens here is that ALU is much smaller, right, than the one on the left-hand side. So again, I'm shrinking the size of the operation. Then I can instantiate many more and thereby achieve the same performance. The beauty of the cost of this one is it saves the resources, but it increases the latency to some extent, right? Because now to do the same operation, it will take a number of cycles to shift all the bits through. So that's kind of the trade-off. So we found by implementing this for matrix multiplies, for example, that the FPGA bit parallel to bit serial gives you roughly the same bit level performance. But the beauty of this is now that you have a chip which can compute with different bit widths. So you can run 2-bit data types, 3-bit data types, whatever you want. So that's the last bit of unconventional architecture. So let's talk about the fundamental design space trade-off that you're going to come up with, right? So by the end of the day, everything that you're going to do comes at a cost. Reduced precision comes at the cost of an error ratio, a loss in error. So again, y-axis is your error percentage. You want to be all the way down at 0% ideally. Of course, that's not possible, but this is where you want to be. On the x-axis, I've put down compute cost. So you don't need to understand how I compute this, but what that basically means is how expensive is it to implement this specific neural network. And please note this is a logarithmic curve, which means everything to the right is really far out to the right. So what we've drawn up here, all these data points, are different types of neural networks. So ResNet 50, AlexNet, GoogleNet, you name them. There's loads of them here. And we've implemented them with different precisions. So the interesting point, so they all solve the same problem. The best solutions in this space are the ones that are the Pareto optimal. So you want to have the ones which have 0% error and minimal compute cost. So you want to be in the lower left-hand corner. And the next best thing that you can do are basically on the Pareto frontier. And then depending on what your application says, so for example, your car might say, I need to have, probably 10% is probably too much. Let's say it's 10%. The car says, I can handle 10% error rate. Okay, I'm only going to crash into 10% of the pedestrians. So let's say that for a moment. Then what I'm doing is I'm basically taking this and look, what is the cheapest one of all these networks that is below the rate? And I would probably pick up this specific dot here. And if I compare this one with this one, for example, these are both ResNet topologies, but this one here is implemented with 8-bit, 8-bit. This one here is a larger ResNet, so this is a 50 compared to 18, but it's implemented with 2-bit, 8-bit. And the beauty of this is that even though the ResNet 50 has a lower precision than the ResNet 80, it actually has better accuracy and smaller resource cost, right? So what I can do is I can compensate for the loss in, or I can recuperate the loss in accuracy by increasing the size of the network. So reducing precision doesn't necessarily mean that you're going to lose error. You increase the error rate. But what it means is there might be other ways that you can actually get that back. You can get your accuracy back by increasing the size of the network. So unconventional with reduced precision can reduce cost and resources, save power, and potentially scale performance. Okay, so with that, I'm not sure where I am on the time axis, but in summary, there's basically machine learning hits technology. Out of this comes this surge of unconventional computing architectures, which are emerging to help with the rollout of machine learning algorithms and make them a practical reality, right, to enable self-driving cars and whatnot. By leveraging customized data flow architectures, reduced precision, and so on, you can really get dramatic performance scaling and energy efficiency benefits, and provide exciting trade-offs within the design space. And that's it. So thanks so much.